They already are. Oh. Email me if you don't find it.
Oh, okay.
Okay? Email me if there's anything you want to see. Okay. I think we're down to 3 now. Almost there. That's correct. Minus. Still minus. Minus doesn't go away. Minuses. The derivative of this. This minus doesn't go away. Well, the lesson seems to be calculators have their limits. We can go over the problem. I mean, there's what they call round off accuracy. You can ask me about the problem. We're gonna go on, but you can ask me about it. All right. Okay. Would someone just check out the back door, make sure everybody's here who wants to be? Oh, I missed somebody. Uh-oh. Sorry. Okay. So, did you want to ask me about that problem? Did you want me to? Which one was that? Was that number 2? Yeah. Integral 1 to infinity of 1 over x to the 4th dx. The limit as a approaches infinity of 1 to a, of 1 over x to the 4th dx equals x to the, what is this? This is going to become x to the minus 3 over, over minus 3, 1 to a. Limit as a goes to infinity. It's going to be minus, yeah, 1 over minus 3a cubed minus a minus 1/3. That limit's still there. And as a goes into infinity, this goes to 0. This is just 1/3. Now, someone pointed out that if you try and figure that out on your calculator, you don't have to go out very far. Yeah. Oh, how did I forget you? I'm sorry. Oops. My apologies. So if you put in calculator 1 over x to the 4th, and you try and calculate from, what is it, 1 to, I don't know, I'm just going to go to 10. Do that. I get 0.3333. 0.33. I get 0.3330001. But there you are. But you got something really wacky, right?
I changed the window and I changed the Xmax to 10,000 something.
It tells you that in this extreme example, the calculation it's doing has some kind of problem, right? Could be round off error. It gets pretty excessive, right?
I mean, so from 1 to 10, if that certain area is C, but if I try to get from 1 to 100, it should be greater than C, right?
Yeah,
but
should be greater than this.
But I got a smaller value.
Beware, calculators can be very useful, but they have their limitations. They're using probably floating point numbers that are accurate to maybe 10 digits. So once you kind of push that, you can get all sorts of weird things. Okay, is anyone else still working? No? Good, okay. I want to go over number 5, and I have selfish reasons for doing this, which I will explain. But first we have to do problem 5. So we have a function 1 over x, 1 over x, and we kind of spin that around so we get a cross section which is pi r squared, which is pi over x squared. And we want to integrate it in part 2 from 1 to infinity. And so what happens here? Just like the other problem, we want to take a limit as a approaches infinity of this 1 to a of pi over x squared dx. And now I do my antiderivative and I get negative pi over x from 1 to a, but we're going to take a going to infinity. And I get negative pi over a minus pi over 1, which is just pi minus pi over a, and I take the limit as a goes to infinity, and I get pi. Okay. So the volume of this tube is pi. That was the answer I was looking for. But the reason I really like this problem is it has an associated problem that we didn't learn how to do. For some odd reason, the department doesn't think surface area is that important. So I'm going to give you just a little brief explanation, which I think should be pretty clear. We take the same function, and we're going to take the same tube, but now we're not interested in the volume, we're interested in the surface area. So the surface area, well, if you think of this as a little dx, right? And this is 1 over x. Well, that's the radius. So 2 pi r is the circumference, and times dx, well, 2 pi r, which is 1 over x, dx is what I'm going to integrate now. And I want to find the surface area out all the way to infinity. Okay? Well, we're going to do the same process. The limit a approaches infinity, 1 to a of 2. Let me take the 2 pi out. Right? It's a constant, 1 over x dx, which of course pi gives me the log of x from 1 to a, which is, let's see, the log of 1 is 0. This is the log of a, so just the log of a, the limit as a goes to infinity. Well, what happens to the log of a as a goes to infinity? It's divergent. Goes to infinity. Goes rather slowly, but it does. And the reason I love this problem is, we're used to thinking of math as a model for the real world. And usually it's a good model. That's why we use it. That's why I invented it. But it kind of doesn't work here. You see, here I've got this long tube that goes out to infinity, and its volume is pi. That means, like, you think of this as an infinitely thin tube, I can fill it up with paint. And I only need pi paint. But if I want to paint the tube, even infinitely thin, I need an infinite amount of paint. It's very strange, It's fascinating, and then it also should serve as a warning that sometimes math, I mean, it makes sense within itself, but it doesn't really make sense outside. So, okay. Is there any questions about this? I just thought it was a really fun problem. All right. All right. We're going to do a little more today. Since it's so late in the quarter, it's not like I expect you to take it home, do homework, come in, get quizzed or tested on it. This is all information that will be useful to anyone continuing in calculus. And it's probably pretty interesting even if you're not going on. What I want to talk about today is, I guess it's chapter 610, where you'll find it in the book. The topic is the hyperbolic functions. We've seen these a little in the class. We haven't really just gone ahead and done anything serious with them. These functions, I think by now you should know the hyperbolic sine is defined as e to the x minus e to the minus x over 2. And the hyperbolic cosine is defined as e to the x plus e to the minus x over 2. And then we have other functions we'll talk about. Hyperbolic tangent, defined just the way you think, sine over the cosine. There's a very special relationship between these functions and the trigonometric functions. That shouldn't be a surprise that we give them the same name. But all these functions fit into a specific category. These are all transcendental. Big scary word. Transcendental. Sounds mystical. So what is a transcendental function? Well, the best way to describe what a transcendental function is to describe what it's not. Right? It's not an algebraic function. Spell this right. Algebraic function. And what's an algebraic function? An algebraic function is a function of the form y or f of x equals some constant a to the n times x to the n plus a to the n minus 1, x to the n minus 1 plus all the way down to a1x plus a naught. It's a polynomial function. Note that n is a finite integer, positive integer. So these are functions that I cannot express this way. That is not to say you cannot express one of these functions as a series like this that happens to be infinite. In particular, I want to show you that a very specific transcendental function, y equals e to the x, can be described this way. If you're taking 1c, you're going to get more of this. We're talking about something called a Taylor series right now. But let's just say, for example, that maybe it's possible to express this as some constant plus another constant times x plus another constant times x squared onwards. A to the n, x to the n, and so forth. So all we really need to know what this series looks like is to know what these A's are. And we can do a little figuring out. We could say, well, what if x is 0? Well, we would have e to the 0, that's 1 equals a naught. So we're already on the right track. We found one of the A's. How do we go forward from here? Well, in the case of a Taylor series, what we do is we find the derivative of both sides of this equation. So the derivative of e to the x, of course, is e to the x. Derivative of a naught is 0. Derivative of a1x is a1. Plus, now here, the derivative is going to be 2a2x squared plus 3a3x cubed onward, all the way up to n, a to the n, x to the n minus 1. Now we can do the same trick. We can set x equals 0, and that tells us that a1 is also equal to 1. Okay? So far, so good. Let's keep going. Maybe we can find a pattern here. Now e to the x is equal to, okay, made a mistake here. This is just x. This is x squared. Okay, so we have, the derivative here is 2a2 plus 6a3x plus n times n minus 1, x to the n minus 2. So now we know that 2a is equal to 1. Again, if we plug in 0. So a2 is equal to a half. I'm just going to do this one more time, because then we're going to see the pattern. E to the x equals 6a3 plus n times n minus 1 times n minus 2, x to the n minus 3. So now a sub 3 is 1/6. Now, if you look at how we've constructed this, you can see that these a's, right, a sub n is actually equal to 1 over n factorial. And that means that I can now express e to the x as 1 plus x over 1 factorial, x squared over 2 factorial, plus x cubed over 3 factorial, and so forth. If you like, and you know how we define 0 factorial as 1, you can write this way. So in the case of e to the x and these other algebraic functions, sines, cosines, hyperbolic functions, we can get an infinite Taylor series. We just know it's not going to be finite. Okay. All right. But back to hyperbolic functions. Actually, back to trig functions for a moment. You know that if we were to take some parametric equations, right? X equals cosine of t, y equals sine of t. And if we were to graph that, we would get exactly this, a circle. That is the coordinates cosine of t, sine of t. Sometimes these functions, the trig functions, are called what? Circular functions. Should give you an idea why. What happens if we instead take the parametric equations x equals hyperbolic sine t and y equals hyperbolic, I reversed it. Again, hyperbolic cosine of t, hyperbolic sine of t. What happens if I graph this? Well, in fact, what I get is a hyperbola. So the naming now suddenly makes a little more sense. I mean, this e to the minus x, e to the x minus e to the minus x, and e to the x plus e to the minus x, that doesn't seem real obvious. But when you realize that this parametric equation is a hyperbola, now that naming seems to make a little more sense. Okay. Here. Something else I want you to think about. We know that the equation of a circle, the radius 1 is x squared plus y squared equals 1. Similarly, for a, I'm going to use the term square, meaning, well, I'll get to what I mean by that in a second. X squared minus y squared equals 1. That's the equation of what? You should all know this. An ellipse? No. But it is a conic. You're on the right track. If I take a circle and I say, I don't know, 1 squared, 2 squared, if these numbers are different, then you get an ellipse. I mean, an ellipse is really a circle. Let me rephrase it. A circle is really an ellipse that's square. Right? So this is the equation of, you guys should know this. Yes, hyperbola. Thank you. All right. Thinking about that, I want you to recall that we have an identity that looks like this. Cosine squared x plus sine squared x equals 1. Well, for the hyperbolic functions, we have a very, very similar identity. Cosine h squared x. At this time, it's minus sine h squared x equals 1. All right. I mentioned that there are other hyperbolic functions, but you already kind of know them, right? Hyperbolic tangent is just the hyperbolic sine. Just take your knowledge of trig functions. Hyperbolic tangent is this hyperbolic sine over the cosine. The hyperbolic cotangent would just be the reciprocal. And of course there's a hyperbolic secant, which is just 1 over the hyperbolic cosine, and hyperbolic cosecant, which is just 1 over the hyperbolic sine. Okay, other similarities between, well, I don't have them up here, between the trig functions and the hyperbolic functions. We know that the cosine minus x is the cosine of what? X. It's an even function. And the sine, it's an odd function. Well, similarly, you can show this very, very easily. Let's do it, right? Hyperbolic cosine of minus x, by definition, is e to the minus x plus e to the minus x over 2, which is just e to the x, switching these in the position. E to the minus x over 2 is just the hyperbolic cosine. So hyperbolic cosine is likewise an even function. Hyperbolic sine, you can show, again, quite easily, is an odd function. It's kind of nice working with these because all these properties we're dealing with pretty much come right out of these definitions over here of the sine, hyperbolic sine, and cosine. Okay, I just want to bring up one more interesting connection between the trig and the hyperbolic functions. Again, there's a lot of kind of symmetry or alternating symmetry or dual symmetry between them. You might think, well, if these are so easy to define, why can't we do that with the sine and the cosine? I mean, the sine and the cosine, we need a calculator, we need to plug in a number, or if there is a Taylor series for it, it's very long and complicated. Well, it turns out that if you're willing to jump into a complex plane and learn some complex algebra, you can find that the sine of x can be defined as e to the ix plus, no, not plus, minus, e to the minus ix over 2. And the cosine is equal to e to the ix plus e to the minus ix over, oh, I made a mistake. Sine is over 2I. And if you use these definitions, you can produce things like this identity here. All the formulas, sine 2x, sine of half of x, they all can come out of these definitions. If you're willing to engage in complex, meaning imaginary numbers. Okay. All right. So much. So little time. Okay, so let's just take a look at. I'm not quite done with the trig functions here yet. I will be shortly, but I want to. We just call these circular for the moment. Hyperbolic. So we know from trigonometry that 1 plus tan squared x equals secant squared x. On the hyperbolic side, it's 1 minus tan squared x equals secant h squared x. Slip that h in there. We have the sum formula. Cosine of x plus y is cosine x cosine y minus sine x sine y. On this side, we have the hyperbolic cosine of x plus y is now hyperbolic cosine of x, hyperbolic cosine of y. I'm going to need more room on this side. Plus hyperbolic sine x, hyperbolic sine y. Okay, I mean, you know, the similarity is kind of astonishing. All we're seeing here is pluses and minuses switching. In the case of the sine formula, x plus y, sine of x plus y is sine x cosine y plus cosine x sine y. And it turns out in this case, for the hyperbolic sine, it's exactly the same. Hyperbolic x, hyperbolic y plus, hyperbolic sine hyperbolic x, cosine hyperbolic y plus cosine hyperbolic x, sine hyperbolic y. All right. So you can go from there and you can, derive hyperbolic sine of 2x, cosine of 2x, half-angle formulas, and so forth. All those good things we learned in trig. And they're very similar, but they're not always identical. But of course, this is a calculus class. We should at least pay a little deference to calculus here for a minute. This we have seen before. The derivative of the hyperbolic sine is the hyperbolic cosine. But unlike the trig functions, derivative of the hyperbolic cosine is just the hyperbolic sine. These are things you can readily verify just using the definition. Other similarities are derivative of the tangent. Hyperbolic tangent is just the hyperbolic secant squared and I'm going to skip the cotangent for now. The hyperbolic secant is the hyperbolic minus the hyperbolic secant times the hyperbolic tangent. So there's a real close connection between these. I don't think it would be complete understanding of all this if we didn't at least look for a minute at the inverse functions. So let's just take inverse hyperbolic function and just think, what could that be? Well, oh, goodness. I had some notes, but they're gone, so I have to do this from memory. Well, let's just write this out for a minute. Y equals e to the x minus e to the minus x over 2. That's the hyperbolic sign. So to find the inverse, we switch the x's and y's, right, and solve for y again. So if I have x equals e to the y minus e minus y over 2, what am I going to do now? Well, let's multiply both sides by 2, and then let's set everything on one side. So we have e to the y minus 2x minus e to the minus y. Not ready to solve for x yet. Let's multiply through by e to the y. So I'm going to get y squared minus 2x e to the y minus 1. And if I look at this, this is actually a quadratic equation, except instead of x, I have e to the y. That's okay. So using the quadratic formula, e to the y is going to be what? So negative 2x, or 2x plus or minus the square root of b squared, which is 4x squared, minus 4, right? Plus 4, all over 2, or x plus or minus the square root of x squared plus 1. Now this plus or minus 1 thing here, right? If you think about it, if we use the minus, the square root of x squared plus 1 is always greater than x. So this would be negative. But there's no way to make e to the y negative. So the minus is an extraneous root. So we can just eliminate that. And now we can solve for y. Y is just the log of, well, it's just the log of x plus the square root of x squared plus 1. So that's my inverse hyperbolic x. We can do something similar with the inverse cosine. Inverse tangent's a little harder. But, you know, here it is. It's a nice straightforward function you can plug into your calculator or use in some formula. It would, however, be nice to know what the derivative is, right? Because that might show up somewhere. Maybe you want to integrate a function that happens to look like that function. So let's just take a quick look, see what we get. So the derivative of inverse sine of x is the derivative, the log of x plus the square root of x squared plus 1. So that's going to be 1 over x plus the square root of x squared plus 1. right? Using the chain rule times this, 1 plus, okay, now I need to find this derivative of the square root of x squared plus 1. So that's going to be 1 over 2 times the, right, x squared plus 1. But I need to use the chain rule again, so times 2x. The 2's cancel. Looks like I can do more here. Times square root of x squared plus 1 times x over the square root of x squared plus 1. Okay. So now we have x square root of x squared plus 1 plus x squared plus 1 all over x square root of x squared plus 1 well, let's divide by the square root of x squared plus 1. So on top I just get x, over here I get x, and here I have the square root of x squared plus 1. It's not what I expect. All right, well, those of you really interested, that can be a homework assignment. Find to properly derive the. I'm really supposed to get 1 over square root of x squared plus 1, which is something you're likely to run into needing an integral of. Okay. So that's kind of the general layout of these functions. One of the things I find curious is that while the trig functions come up very naturally when we're doing geometry, you know, there are lots of problems like lots of problems where, you know, you have a flagpole and, you go 100 feet from it. You want to know how tall it is, right? So you measure this angle, and now you can figure out the height. But you haven't run into anything where these hyperbolic functions come in. So in order to provide such an example, we're going to have to talk about a special curve called a catenary. Catenary is kind of a curve that looks a little like this. It turns out it's the curve that if you have a piece of rope and you're hanging the rope follows the curve of the catenary. Now you might say, wait a minute, that doesn't sound right. I know, for example, that the Golden Gate Bridge, suspension bridge, right? That this is not a catenary. Does anyone know what the curve the cables on the bridge follow? Okay. Well, this is a parabola, right? But the important difference is that the Golden Gate Bridge is a suspension bridge, and it has cables coming down that are pulling it, and that's how you get a parabola. If you just hang a rope, you're going to get a catenary. And the catenary function looks like this. It looks like a hyperbolic cosine of x over a. It's a hyperbolic function. So, okay, so let's just do one. We'll just do one problem having to do with a catenary. We're going to take kind of a mountaineering kind of a thing. We have two mountains near each other, and we tie a rope across them, and we're going to hook up our lines, and we're going to swing across. And the distance here is 100 feet. And we're going to set up the axis so this is 0. And so the formula for this rope here is just y equals 200 hyperbolic cosine of x over 200. You have to think of the y-axis as going down. Otherwise, I need a negative sign. And the question is, so what is the length of this rope? Given this formula. Okay, does anyone remember how we figure out the length of a curve? Anyone remember the formula? If I have some function f of x, my length is the integral of what? Uh-oh, only one person knows, yes.
The root of 1.
Yeah. Look this up before the final. 1 plus.
1 plus something.
We can put that on the final. It's 1 plus something. Derivative. But it's the derivative squared. Okay, let's push this over. Okay. So that was the hard part. Here comes the easy part. So we're integrating here, since this is the center, it's from minus 50 to plus 50. Integral of square root of 1 plus, okay, now we need the derivative of this. Well, the derivative of the hyperbolic cosine is the hyperbolic sine. So it's 200 hyperbolic sine of x over 200 times 1 over 200. This is going to cancel. So that's going to be 1 plus hyperbolic sine squared x over 200. Okay. Dx. So maybe a good substitution would be what? U equals guesses? How about x over 200? So du is equal to dx over 200. So what happens to minus 50 and 50? Minus 50 becomes, plug in minus 50 here, minus a quarter, plus 50 becomes plus a quarter. This becomes the square root of 1 plus sin h u squared. And dx becomes 200 du. Okay? But if you remember, 1 plus the hyperbolic sine squared is hyperbolic cosine. Square root of it is just hyperbolic cosine. Oh, let's even skip that step. We're running out of time. So the antiderivative of the hyperbolic cosine is just the hyperbolic sine. Back again. U. Minus a quarter, 1 quarter. Right? So that's 200 e to the 1 quarter minus e to the minus 1 quarter over 2 minus e to the minus 1 quarter, keep writing 1/2, minus e to the 1 quarter over 2. So we get 2 of these and none of these. So it's just 200 e to the 1 quarter, which if you want to plug it into your calculator, it's 101 feet about. Thank you all. I will see you Thursday. Please come in with questions, and I'll be here for a little while if you have questions today.